This lecture introduces the row echelon form of a matrix. So by the definitions, a matrix is said to be in the row echelon form if the first non-zero entry in each non-zero row is 1. What does that mean? That means if you have, let's say, if you have a matrix, let's say 4 by 4 matrix, okay? So then if you have a row that is not a non-zero row, so what is a zero row? A zero row is a row that contains all zeros as its entries, right? So I have 4 columns here, and I have 4 entries, 4 0 as the 4 0 entry of this row. That means this is a zero row. So that K is the row. So K row, so K equals 4, and then K is a 0 row. All right. So then if I have a non-zero row, let's say the first row is non-zero row, then the first non-zero entry has to be 1. And then all the entries of this row can be any value, but the first non-zero entry has to be 1. Okay. And then the second condition is if row K does not contain all zeros. That means if row K equals to 1, is not a 0 row, then in row K plus 2, which is K plus 1, which is row 2, in row 2 has to have at least 1, or has to have the number of leading 0 entries, right, in row K plus 1 is greater than the number of leading 0 entries in row K. So consider K equals to 1. The first row has no leading 0 entry, right? Because the leading entry is non-zero. So the number of leading 0 entry is 0. That means in the second row, the number of leading 0 entries has to be at least 1. You have 1 as a leading 0 entry. At least, right? It doesn't have to be exactly 1, but at least 1. You can have 2, 3, or 4, and so on and so forth. But consider in this case, the number of leading 0 entry of the second row is 1. Then the next entry has to be 1 because it's the first non-zero entry. And by the first condition, it has to be 1. And then the rest of the entries can be any value, right? Depending on the matrix. How about when we look at the third equation, the third row, K equals to 3, right? Then you know that since on the previous row, the number of leading 0 entries is 1, that means the number of leading 0 entries in the third equation or the third row has to be at least 2, because it has to be greater than. So it has to be at least 2. 0, at least doesn't have to be exact 2, so you can have another leading 0 entry, right? And then the next entry, if it's not 0, it has to be 1 here. All right, so because on the first conditions, the first non-zero entry has to be 1. All right, and then the last conditions is if a row contains all 0, it has to be below all the non-zero row entry. That means if you have a 0 row, all the 0 row has to be in the bottom of your matrix. Okay. Well, let's look at the example number 3, right? We want to consider these 4 matrices. And then you want to determine whether they are in the row echelon form. The first one, the first non-zero entry is 1. Good. The second row, the first non-zero entry is 1. The third row, the first non-zero entry is 1. So the first condition is satisfying. The second condition, see that the second row has more leading zero entry than the first row. And the third row has more leading zero entries compared to the second row. So the second condition is satisfying. Third condition is if you have any zero rows, it has to be in the bottom, which we don't have it here. So then yes, it's in the row echelon form. All right. And then you look at the second matrix. Yes, the first non-zero entry of the first row is 1, which is good. But then here on the second row, the first non-zero entry is not 1, it's 3. So then no, it's not in the row echelon form. Okay? So second condition is violated. How about the third one? The third one, the first non-zero entry of the first equation is not 1. So the first condition is already violated. How about the fourth one? The fourth one is saying, well, we can see that the first non-zero entry of the first row is 1, and the first non-zero entry of the second row is 1. So the first condition is satisfied. About the second condition, the second row, you have no leading zero entry, but on the first equation, on the first row, you have 1 leading zero entry. So this is violated the second conditions. So the answer is no, right? So only the first matrix is in the row echelon form. And then now we can talk about the Gaussian eliminations. So by the definition, Gaussian eliminations is the transforming of a linear system into augmented matrix that is in row echelon form. Okay, so you're transforming a linear system into its augmented matrix, and then you have to transform that augmented matrix into the row echelon form. So that is the Gaussian elimination process. Now, if we look at these examples here, if we look at the 3 matrices that are not in the row echelon form, can we transform them into the row echelon form? So for the second matrix, so the first row is in the good conditions, the last row is just the 0 row, which is in the bottom, which is good, but then the second row needed to be fixed, right? And 3, we need to make 3 to 1, because in row echelon form, the first non-zero leading entry has to be 1. How can we make 3 becomes 1? We use one of the row elementary row operations. So we take row 2 divided by 3, because 3 divided by 3 is 1. So the new row 2 will be 0, 0, 1. All right. Now go to the next matrix. 2 is a problem, 3 is a problem, 1 is a good one. So the last row is in the good conditions, and we check the number of leading 0 entries are good because the second row has 1, the third row has 2, 0 as a leading entry. So it's good. The only problem that we need to make this equals to 1, and we need to make this entries becomes 1, right? And we can do it simultaneously here. When you take row 1, it's the same as row 1 divided by 2, and row 2 is the same as row 2 divided by 3. So then the new row 1 will be 1, 1, 3 over 2. The new row 2 will be 0, 1, and 5 over 3, and we keep row 3 as it is. Okay. And the last matrix we want to do, so the non-leading entries are in a good shape because they are both 1, but then the order is a bit backward. In order to fix this, we just need to use the first row operations when we can just interchange the 2 rows. So after interchanging row 1 and row 2, we have 1, 0 as the first row and 0, 1 as the second row. right? And at this point, the non-zero entries are 1 in each row, and then the number of leading zero entry in the second row is more than number of leading zero entry in the first row. So we in the row echelon form, yes. This is in the row echelon form, yes, and this is also in the row echelon form. So as you can see that given any matrices, you can always transform those matrices into its row echelon form by these definitions. All right, and again, Gaussian eliminations is a process that when you transform a linear system into its augmented matrix, and then you have to transform this augmented matrix into the row echelon form.